Hello. Okay, so we're here to talk to you about how we visualize multidimensional climate data in web maps. So yeah, we work at CarbonPlan, and at CarbonPlan, as mentioned, we work to improve the transparency and scientific integrity of climate solutions through open data and tools. And in climate, that means a lot of web tools. Or a lot of web tools and a lot of web mapping tools. So I'm going to walk through an initial approach we took to doing this web mapping, then step through a new mapping approach we've developed, and then Shane is going to come up here and talk about our latest map release, which came out on Tuesday. So how we started off doing this mapping. This is a project we did in 2021 that maps. Let me get my cursor going. That maps risks to forest carbon. So we have fire, we have drought, we have insects, and we have different warming scenarios. So low, medium, and high. And this is projected over the century. So pretty grim data, but you see a lot of orange, but kind of a neat mapping use case. How we built this, we converted this gridded raster data set that folks on our team built to GeoJSON, and then we created vector tiles. For each of those gridded data points, we mapped them to a collection of points in the vector tiles that each had multiple properties, so those different warming scenarios, the different years of the century, and then we render those map tiles with Mapbox.gl.js. This worked great for getting like a lot of rendering customization, pretty zippy overlays and panning through time with a small set of vector tiles. But we did kind of struggle every time with the special munging process and the intermediate data format going from GeoJSON to vector tiles, doing some like artful, slippy, or to-be-canoe work at the end there. And the point property access pattern was like not the easiest for the different, like all the dimensions of data and accessing those on the fly on the front end. So taking a step back and thinking about in climate, what type of data we're working with, it's often multidimensional and it's often gridded. So we can think of this example of a temperature data set that varies over space and time. Yeah, really important idea of it being gridded. Where like the experiments often are run at the grid cell level, and this is just a very natural way of thinking about these data. On the analysis side, researchers on our team and in the open source community have come up with really great tools for working with these data. So an analysis format that we use is called Zarr, and Zarr is a format for chunking your data, so kind of breaking it down into little slices of data that you can store separately. And within each of those little slices or chunks, they're compressed. And this is a format that scales to arbitrary dimensions or n dimensions. And this is a really great pattern for efficient access. You can plop this data on the cloud, so in like AWS or Azure, wherever you want to put it. And then when you're working with the data, because it's like subset, you can transfer just the chunks you need to work with. So returning to this temperature example, let's say I just want to do like a monthly aggregation. Instead of fetching the whole big data set, I can just grab a slice in time, do my aggregation, and not even touch the rest of the data. And then, I mean, if the data is chunked appropriately, you could also just grab a little spatial slice, which starts, if you are familiar with mapping tiles, might start to turn some gears. It turned hours. So this idea led us to think about a new mapping approach where we would use Zarr to kind of use it with a chunking scheme that mimics slippy tile conventions and then pyramid them, so like create multiple copies at different resolutions, project it to WebMercator for some mapping requirements, which I'll get into in a bit, and then this is just like a standardized set of requirements that we were able to put into a really small Python utility called ndpyramid to produce Zarr pyramids that meet these requirements. This is an example of the processing script that you would run using this ND pyramid library. Quite small, could be done in a Jupyter notebook, stays in the world of like the way we typically work with our data. And then the output from this ND pyramid process is some file structure like this. So we have average temperature with a 0 zoom level with 1 chunk of data, and then 1 zoom level where it increases, and this resembles a map tile server directory. On the front-end side, we used a React component library, which we called CarbonPlan maps, which uses WebGL to render data that is fetched from these numeric chunks which have that numeric data, that are the chunks of the Zarr stores. And then we synchronize what chunks we need to fetch when with a Mapbox.gl web interface. This is what some React code looks like using this CarbonPlan maps library. So for every data cube that we want to access, we render one of these raster components, point it at that ND pyramid output, pass it some color limits, pass it a color map, tell it what variable we want to map, because we could have multiple variables stored in a single Zarr store, and then we wrap that up in a map component, and that handles that Mapbox.gl synchronization. And so we get something like this. Let me turn on my tile boundary. So these are just Mapbox.gl tile boundaries, but they also delineate where the different Zarr chunks are. I can pan around, go deeper into my pyramid, and I can make, because we're working with this, we're fetching these numeric chunks, I can make a bunch of customizations on the fly. So I can change my color map, I can switch color mode, I can change my color limits, things like that. And all just using that same data and like changing what happens on the GPU. A couple examples to step through for like what this pattern, what flexibility this pattern lends you. That example I just showed, just looking at one time slice. Here, if you have a data set that's 3D, so it also has time, we can pan through time, where each chunk includes all of the time steps. We're benefiting a lot from compression here, so data loaded pretty quickly, panning through time, and on the React side, just like passing in a different pointer to what month I want to see. Again, fetching numeric data, so we can do things like query the map data, so not hitting a separate endpoint, just grabbing the values from the map tiles themselves, and getting a nice little JavaScript object that I can like render a time series with, or do some little math. More visual customizations. We have a couple different modes that do fun different things on the shader, or on the GPU. So we have that texture shader, which we've been looking at. We have a grid, we have a dot grid. And then a final fun customization we can make is running this on the GPU. We have a bit of shader code that makes that happen. We can also customize the shader code. So here I've wired up just a basic like temperature minimum below which we skip rendering. So we're eliminating the cold areas of the world. And we can do that with just a really simple if statement. And this happens super performantly over all pixels of the map because it's running on the GPU. Okay, getting into some examples of things we've built with this. This is the first thing we built with it. It maps forest carbon emissions over the world, resembles that forest risk map to some extent. And the key thing for us, we have some slow data coming in, is how quickly we were able to get this up and running. Like, I think it took a couple days because that data processing was so standardized, and we got a pretty similar result. A more complicated map, which also might take a, okay, we're good, maps the potential of seaweed farming as a climate solution, so as a way to maybe draw down carbon from the atmosphere by sinking it or harvesting it and turning it into things like biofuels. This is a techno-economic model that folks at UCI, or California Irvine, developed. And we thought it would be cool to build a map that allows you to play with the parameters of that model in the web. So we're really leveraging this on-the-fly customization and rendering here by fetching a bunch of input layers that are all spatial in nature, so depth, wave height, how far the nearest port is, lots of really fun layers, and then calculating the removal cost for growing seaweed, cost per ton of growing seaweed at any location, and taking into account a bunch of different parameters in the model. And yeah, so going back to that fragment shader customization, we're really relying on that here to get, to recalculate the model over all pixels of the ocean super quickly. So a neat and kind of complicated map that really leveraged this approach. Okay, and now I'm going to hand it to Shane, who's going to talk through our newest map.
Cool. So yeah, this new map just came out on Tuesday, and yeah, pretty excited about it. It kind of hopefully showcases a lot of what Kata just showed you, the power of this this tooling we built. So this is looking at an ocean alkalinity enhancement potential solution to some carbon drawdown that is becoming more and more looked at, but there's not a lot of transparency in data or a lot of work that's gone into looking at how we can monitor or understand how that system would work. And so we partnered with another nonprofit called Seaworthy that did some really cool modeling efforts. But yeah, we have this whole explainer, really worth checking out if you're interested in a little bit more of that. There's some really cool interactive figures in this as well. So this project was with Seaworthy. They did the modeling and we kind of did the visualization in this collaboration. So really big study of almost 700 different ocean regions, each with 4 different injection times. So they're trying to figure out where in the ocean is more or less efficient to add some alkalinity to draw down some carbon. And this simulation has 15 years of data, monthly resolution. There's tons of variables in it to be mapped, and yeah, resulted in a pretty big Zarr store for us to try to get on the web, this half a terabyte thing. So this is kind of a look at how that raster component that we were looking at earlier can get a little bit more complicated when you have more dimensions to your data. And so in this case, we have a selector we're choosing a specific polygon, so a specific region out of those 700, and an injection date, so which part of the year did we inject, that alkalinity, and then time-based things, so the month and year, and then a little band so we can show the total values versus the change that was seen in this specific experiment. And so that's slicing down all of those selector values, cut it down to map tiles that are 150 kilobytes out of that giant store. So pretty efficient. So this is, yeah, our new tool. What we're showing here is all of the 700 polygons, and the color is that efficiency. So how much CO2 drawdown do you get per unit of alkalinity that you added in that area? And so some interesting spatial patterns. We can change the injection time to see how those patterns change. So in the poles, you can see they kind of shift with different seasons, probably from meltwater or different ocean circulation things that we'll explore in a second once we click into a polygon. We've got this kind of nice coupled visualization here to see the individual curves of how carbon is uptaken into the ocean as we've gone through there. So now let's select into a specific polygon and we can see how one of the model results for that specific area. So we've clicked in, we've loaded those map tiles for this chunk of the Zarr, and now we have all these time slices loaded onto the browser so we can very performantly just slide through time. No more network requests happening, it's just already in there. So really smooth feeling animations can come out of this. And like I said, there's a lot of different variables to map with this data set. So things like dissolved inorganic carbon. This is one that's like a full depth instead of just the surface. So you can see a different kind of some more structure come out in different patterns there. We're leveraging that region querying tool. So I can bring up, slipped over here. I can bring up that query tool to build a time series here of how that region of the ocean is affected through this plume moving around through it. And with some custom shader code, we were able to just add, with a little bit of log scale math, we can toggle this over to a log scale, change our color map, and kind of have a different view of the data relatively easily. Again, with no more, it's all the same map tiles. Like, we don't have to build a bunch of different map tiles to show these different rendering options, which is kind of nice. So there's a ton, obviously. I don't think there's no one on Earth yet who has looked at all of these different plumes and just seen how they go through the ocean. Lots of cool ocean dynamics to explore in this. So yeah, it was a really fun data set to work with, just because it's so pretty to look at as you're doing your workday. So yeah, this mapping tool, it's open source. It's on GitHub. And there's some pretty good docs. We'd be really excited to think more about this kind of work with other people who are thinking along these lines. We're still exploring what directions to take this in the future. But things that we know we're kind of thinking towards is like bringing your own mapping library, currently tied to a specific version of Mapbox.gl, but it'd be cool if you could bring MapLibre and not be tied to what we've got tied up in there. Similarly, decoupling it from React, so you could bring your own stack and not have to rely on using a React stack for using this. And of course, like as was demonstrated in this data set that's so global, that the limitation of web Mercator is not ideal in this situation either. So a lot of this would benefit from having the ability to do some more projection work. But yeah, please try it out, and yeah, come talk to us. We'd love to think about this with you if you're thinking about similar things. So thanks.
And we have time for a couple of questions if people have them. I don't know if we have a microphone that can be passed around, and this one's attached. So I guess just, so I guess just scream, and we'll do our best.
Yeah, I'll repeat the question.
Well, first, I'd like to say most of the benefit of most of this that things are like that seem to have multi-dimensional arrays. It's like not probably so far anything it should be. But my question is, and this is the first time I've ever seen Zarr in the context of like a I don't want to say like production deployed web visualization, and I'm curious to learn what limitations you encountered when you went to actually go deploy this in a way that was performant for people all around the world potentially looking at it. Like, did you find any limitations with serving directly out of buckets? Were there anything? How sensitive was the structure of the Zarr to the production deployment and performance? I'm curious to learn about those kinds of questions. And if this is too long of an answer,
Yeah. Try it again.
Yeah, you can try. Yeah, that's a great question. I think there are a couple ways, like areas where we think about performance. I think a big one is often a collaborate. We had that small snippet of like how we create the Zarr store we want. I think in reality there's a bit of an art to that. Like Shane showed, really smooth panning through years in the OAE map, and that was because we kind of tactfully picked a chunking scheme that maybe is a little bit unnatural for analysis, but really works well for the web, and then did some math to make sure that the resulting map tiles would be the nice kilobyte range of that Shane talked about. So I think trial and error there, and sometimes there are trade-offs that you have to make, and we take the hit on the web side. But I think that's the big one that comes to mind.
Yeah, I would just say it's very rare that the analysis Zarr is in the right shape that gets you the best performance possible. So you often have to do a rev to get there. But yeah, it's usually possible.